So, first, the overview of the steps. We saw how a crystal can be grown, what are the different methods by which you can grow a crystal. Your protein has to be as pure as possible, or it has to be in the purest form, and depending on temperature, depending on the pH, depending on the buffer, your crystal slightly starts growing. And as your crystal grows and it is ready, then you take that crystal and you put it in a X-ray diffractometer, so where your X-ray beam is passing through your sample, and once this X-ray beam passes through the sample, it gets diffracted, and this diffraction pattern is collected in the form of images. I'll show you some of the images today. And these images are taken in different rotations at a different angle by changing the angle of the detector and as well as the X-ray beam onto the same sample, so that you get onto different angles, and the exact pattern in multiple images comes out, from where you have to understand the structure. That is the main idea. But in this process, what we are getting, we had a wave, we saw the wavelength, we saw the amplitude of the wave. When two waves of the same phase matching with each other, the amplitude doubles. That is a constructive interference. When the two waves with difference in amplitude, difference in phase, they together, when they come together, then there is a negative effect or a subtractive effect, and it becomes a destructive interference. And these patterns of constructive as well as destructive interference is what we get it. But the important thing I had been telling is the phase, if they are in the same phase or if you're not in the same phase, right? So the problem with phase, what is the problem with phase, and how phase can give us a much better idea about the structural details, that we are going to see it. Once we solve this phase problem, then we will see how we can calculate the electron density map, and based on the electron density map, which again is deciphered information, or the information which is already hidden in the X-ray diffraction pattern. So from this pattern we will try to calculate the electron density map, and constructing a structural model out of that electron density map is the goal. And once we have constructed a rough construction of the model of the structural you have identified or you have built it, then it comes refining of the structure, so that that structure is as similar or it's very close to the actual structure which you are studying it. And how you are going to do it, that we are going to show today. So if you remember Bragg's law, these are the planes that you can see. This is one plane, this is another plane, and when the light is falling, or not light here, sorry, the X-ray beams are falling, and you see when it falls here, you have an angle of diffraction, and this angle theta, you see this angle theta is the angle of diffraction which is calculated. And as we go deep inside, then we say in the multiple planes how the extra wavelength, or how the like one particular change. So from this wavelength and this wavelength, there is an addition wavelength here, because this is the addition distance which the X-rays have to travel within the crystal lattice. Now this looks very simple, and it explains typically in one dimensional structure. So one dimensional structure meaning you can see multiple of these planes, and we can go deep inside and find out, right? But that is not the actual story when it comes to structural elucidation. It is, the structures are not as simple as you can just find the alpha, you can just find the lambda and the distance d between them. No, it is not as that simple. So to understand it in a little better way, we have or I'll try to show it in the form of a vector. So when you have, this is a space, or this is a spatial representation. In this spatial representation you have the x-axis and the y-axis, and you have 2 points. Now apparently in a one particular plane, these 2 points looks like they are in the same x-axis. You see, in the same x-axis, in the same, so this is like fixed coordinate, it's just one plane. But that's not true when you talk of the lattices. So when we talk of the lattices, so this is one reflection in one dimension, we are getting it. But when we change this, so when we change the dimension and a 2D reflection, we get something like this, which is much different from the previous two images. And this is actually, in form of three vectors, which you can say as Miller indices, and they're represented as, if you think of a crystal, you can just think of the height, width, length. So in the same way, you have the H, the height, the length, and then the width. So H, K, L, these are the three vectors which will define, and they are named as Miller indices. They define the integer number of the wavelength that result in an observed reflection from a 3D crystal. Okay, so take for example, this is a simple cube, and in this simple cube, if I take one unique reflection plane, so one unique reflection plane can be this plane, it can be this plane, or it can be this. But if you think of just the surface or just the outline of it, then you are missing out the internal informations or the volumetric informations. So for example, if you're considering this plane, you see here there can be another plane here, because depending on the lattice structure, there can be one atom in the center position, right? So this can be one plane, you can see here, or it can connect these two coordinates, so you can see these two ends inside, or it can be from the other side. So three planes you can find it here. Another way, if you want to do diagonally, yes, diagonally you can see from this plane to this plane, all the diagonal planes are attached. Here also diagonal planes, here also diagonal planes. Now if we think of just having HLK, so HLK is basically H, this one, or XYZ, HLK and XYZ you can just think as same. So you see here X, Y and Z. So these three planes are there, but they are not defining these internal planes, and that is why the difference. So first of all, we'll see with HLK, and then we'll see the difference, how we can decipher these internal planes also if we move ahead. So coming to Miller indices, in a 3D diffraction, what you know is HKL, and this HKL can be represented in different 2D plots, and when you convert them in a function, so in a function when you convert them, and you see they are different spots, they are created different spots of Miller indices, from the Miller indices, right? And this patterns, basically we are getting spots, so from the spots we have to decipher backside. Basically the idea is you have to find out the structure of the crystal from the spots of the diffracted X-rays which you are getting it. So if you have to understand the diffraction, then if you understand the pattern of diffraction, then you can trace back to the 2D structure or the 3D structure of it. Now when you see, this is an example of X-ray diffraction pattern from the sperm well myoglobin crystal, and in this myoglobin crystal, you see this is from one particular angle you have got this pattern, diffraction photograph. Now this contains information from all the atoms, right? And the pattern of the spots, the diffraction pattern, basically it will allow to determine what? It will allow to determine the crystal parameters, like the size of the unit cell, the symmetry within the unit cell, the distance between them. So basically we are trying to find out the crystal of, or basically a small unit cell from the crystal, right? And how we are going to do it? Yes, I'll come to that, but idea is very simple. From this pattern you have to find out or retrace the structure of the unit crystal cell. Now structural informations has to be derived, yes, that we understand. And if you see here closely, some spots are very dark and some spots are very light. You see the spots are not same, they are different in intensities, yes. And from this pattern and intensity together, what you have to obtain is, you have to obtain information, okay, which will have the diffraction photograph taken, or multiple images of this sample has been taken at a different angles, and from this separate angles, if there are like 20 different different images are there of the myoglobin crystal, and then from this 20 different crystals images, what you have to do is you have to decipher this information. Okay, so how we are going to do it? Okay, like it looks like pretty simple. Like from this multiple images I will get an image which is like this, based on some of the software help, and this will give me the electron density pattern. Based on the electron density pattern I can predict a structure which will be like the actual protein structure of my sample. Okay, so if it is that simple, then things would have been pretty good. I think that would have been, everybody would have loved it. But unfortunately it is not that simple. So let's try to understand why the phase problem, what is the importance of phase, and how we can rectify, or how we can experimentally phase problem can be removed or tackled in the best possible way, how you're going to manage it, right? So in a structural factor, as I was telling, you have this wave. In the wave you have the information as the amplitude. So amplitude is the function f in HKL. So now we are all talking in terms of vector. So in terms of vector, as I said, 3 vector directions are there, HKL in the crystal, and from this HKL the function is the amplitude. This is the function of the amplitude, and also we have the phase function. So in the phase, you can see here, this also is an important thing which you can predict it, yes, but in this scenario we are able to find only the amplitude intensity based on the intensity, what the spot intensity. If the spot, like in this case, you have the spot darker, lighter, so these are basically the intensity differences. So when based on this intensity we can have an expression and we can find out the amplitude of it. But what about the phase? And this phase information is missing here. You see, the phase actually gives you the angular informations. So this entire angular information is missing, and once this is missing, you cannot have structure, and it cannot predict the structure absolutely, right? So why phase is so important? Now if you see here, this is a duck, this is a cat. Okay, now if we just take the amplitude information from the X-ray diffracted images, and from there if you try to backtrace the structure, you will get an image of the duck somewhere like this. Okay, so this image of the duck, it do not have a full structural information onto it. On the other hand, if you see the phase information, because the phase information you see in the cat transformation, it is much more clearer in forms of structure, so you can at least find out this is the animal, this is the cat. Okay, in the previous case you are not able to find out, right? So just knowing the intensity is not good enough, and that is why we have to come up with a something where we can decipher the information of the, and this is commonly known as a phase problem. Okay, so this is commonly termed as a phase problem. Now it is I slightly differ. It is not a problem, but this information is missing. We have to find out ways to take this information out. That's it, right? So first is function of the intensity. So first is structural factor, and from there we are going to see how the function of the intensity is going to be deciphered. Now, how to get the electron density map from the intensities of reflections? That is the question, right? What we have is electron density, you can have is as this expression, and this is directly related to the intrinsic amplitude of the scattered X-ray from each type of atom, right? So this is dependent on this factor. Now based on the intensity, like higher the intensity, lower is the electron density, more or it's inversely proportional. So higher the intensity, more is the, or less is the electron density, and more the electron density, the less will be the slight spot or the X-ray spot coming onto your images. Okay, now if we do a summation of this atomic scattering vectors. Now what we are doing is we are doing a summation. So this is a function of HKL, as I was telling, and we are doing a summation of this atomic scattering of these vectors, and the molecular scattering factor is F. Also you can tell this as a structure factor, and from this structure factor we are going to calculate with this expression where x, y, z information is taken by default from the lattice information, and with this you see in the HKL information along with the XYZ information has been put into a transformation expression from where the calculation will be done. Okay, so there will be some mathematical expressions in today's talk. If they are like, if you have problem in understanding them, just take it simply that why we are doing it, because nowadays you have softwares and they take care of all this expression and simulation part automatically. Okay, now to continue with that, what you have is a Fourier transformation that we were trying to do it. So this is the expression, and from this function or molecular scattering factor F, from this what we are trying to do is we are trying to find an expression in the Fourier transformation, and what the magnitude of F, we have to understand, is proportional to the square root of the intensity. So this function, structural function, is proportional to the square root of the intensity, which you can see here, mod of F HKL is proportional to the square root of the intensity here, right? Now in this expression, so this is the final expression which we can draw or which we can find out. We have the electron density. Yes, we have the electron density here. We have the intensity parameter here, and we also want to have the phase information. But this phase information in this particular thing or expression will be missing. So if we convert it from the structural this F function, if we convert it, Fourier transform it, we will get information from the intensity, we will correspondingly get the electron density, but what we will be missing is we will be missing the phase information. And this information, how we can get it, so we'll see by different expressions how different people have tried to put it or represent it in different form of mathematical expressions to get this the phase informations. Okay, so first the vector space interpretation. Now Fourier summation of all measured intensities with all phases is for example taken as 0 degree. So we are assuming it right at the beginning that the summation of all measured intensities with all phases are equal to 0 degree, and based on that we will try to do it as a Patterson map. Okay, so when you're doing as a Patterson map, what is the difference and why we are doing it in Patterson map? So electron density, we saw this expression, right? So you see this expression where you have the amplitude but the vector information or the phase information is missing. When you have a Patterson function, in the Patterson function you see x, y, z are changed with u, v, w. Now what is this u, v, w, and what is how it is different from x, y, z? In x, y, z we had distances between the atoms, right? So we had different distances between the atoms which are neighboring to each other. But in u, v, w, you have the differences between the atoms in all the planes, which is even they are not neighboring to each other. So they may not be in the same plane. So x, y, z essentially in the same plane, the neighboring atoms are being, the difference or the distance between the neighboring atoms are taken into consideration. But in u, v, w, atom and all the plane, all the atoms surrounding that particular atom in any plane will be taken into expression, and that is where you have a much better understanding in the volumetric part. Now why this is important, because when you talk of a single plane like x, y, z, in one plane I have two atoms, they are in the same plane and I can find out the correlation between them, but I am missing the angular information with respect to other atoms. But in case of u, v, w or the Patterson expression where you see here, in this expression it has taken into consideration all the angular aspects or of the particular atom and its all neighboring atoms, maybe in different angles, maybe in different planes, all are taken into consideration and they are expressed. Now, so we have the structure factors, right? And what we do is we know the electron density, so we do a Fourier synthesis, and basically what the expression I showed, that is a Fourier expression by which you get the electron density, and you do like a second or an inverse or a Fourier transformation rather to get the structure. So basically you get the pattern, from the pattern you do a Fourier transformation, you get the electron density, and from the electron density you do a Fourier transformation and back to the structure of the crystal or the unit cell which you are looking for. Okay, now let make things little bit complicated. Okay, why I'm saying complicated? Because we have to also get the Patterson map into picture. So how you are going to get the Patterson map? In the previous one, amplitude to electron density and back to amplitude, but this phase information was somewhere missing. So what we are doing is, in this case we are assuming in the first case that the phase is 0. So assume that they are all in the same phase and the angle is 0 degree. In that condition, we will do it with respect to not with electron density, but with respect to the Patterson map or the Patterson expression. Once you do it in the Patterson expression, then we have by default taken the phase or the adjacent atoms, right, at different angles. And then what we do is we do a Fourier transformation, and once you do a Fourier transformation we come back to the structural pattern where we will have the phase information also. Okay, now to do this, if I say just by doing changing the expression level, taking from x, y, z to u, v, w will help it or will solve this purpose? No, not absolutely. For that we have to do certain methods, and by taking care of those methods, what will happen, we will try to get this phase problem removed in a much better way, because just by changing the expression we will not get much information and will end up getting nothing, right? So there is something called molecular replacement. Now molecular replacement is a method where what is basically it will have a similar structure, it will maybe a homologous structure, and it will match. So the search model, suppose you are predicting a model, right? And once this model, how a prediction will be, you search it with a very close looking model in terms of structure wise, and then you try to match with it. So a similar structure, okay, in the form of a search model, we have to develop few search models. How we are going to you optimize different search models and get us similar structure, okay, and place it. So once we are able to get that initial structure or the unit cell, right, you try to place it in your sample, okay, and get the initial phases, right? So the idea is, what is molecular replacement is, suppose you are studied, you have got the initial structure from the library, from using the software you find out a similar structure, take that structure, take the unit cell, try to fit it in your model and try to obtain the initial phase information, right? So this is usually the first method of choice of most of the crystallographers, right? And it often happens as part of an automatic pipeline, so that you cannot see it. Means the software algorithm these days, they don't tell you, they will do this automatically, right? Okay, now let's understand this molecular replacement at a depth. Okay, so if you go by this, it is basically used to describe the use of an unknown molecular model, okay, to solve the known crystal structure of a related molecule. So two things: unknown molecular model, that is already understood, or you have to solve you have understood a partially you have got a structure of that molecular model, and that you are trying to solve the unknown crystal structure of a related molecule. So it has to be a related molecule, with that you are trying to solve the structure. Okay, now molecular replacement will enable the solution of a crystallographic phase problem by providing initial estimates of the phases of the new structure from a previously known structure. That's what I was telling. So from the previously known structure, once you fit that unit cell into your model, you will get an initial estimate of the phases. Okay, and it is much opposite to the other two main methods. So there are other methods also, experiment methods. I'll come to it slowly, where you do it with isomorphous, you do with anomalous. So there are direct methods. So I'll come to it one by one. But here, this is the basic idea. It's very simple. You put your structure, you identify a similar structure, try to fit that structure into your model, and once it is very close fit, you try to get the phase information from that model. Okay. So the use of MR has naturally become more common as the database of known structure is expanding, because earlier, initial time, people didn't had much understanding. They had to do it all like hit and trial and do it repeatedly to get that final structure which is in the final refinement form. But nowadays we have a lot of library, and in that library it is expanding on day-to-day basis. So what you have to do is you have to just go to that library, take your model, try to fit get a closely fitting model, known structure, get the phase information out of it, right? So MR is currently used to solve almost 80% of deposited macromolecular structures. That is huge, right? That is how the replacement. But how do you search, right? So as I said, you have to search it. So this is basically a searching in the library. So there are two methods. I'll just go one by one, or basically I'll tell you the basic one, that is 3x3 method. You can also have a 6x6 method also, but 3x3 model and 3 is pretty simple, and I think that will give you a fair idea. Okay, so in this 3x3 model, what is the positioning of the search model is 6-dimensional problem. That is, you have to understand, 6-dimensional problem. That is why 3x3. Okay, so why 6x6? Now for each, if you see, for each of the molecule, there what you have a 3 degree of rotational freedom, 3 degree of translational freedoms. So you have to understand this 3 plus 3, and then only you will understand the 6-dimensional problem. Okay, so let's divide into two smaller problems. Not to that. So just I was talking of rotational problem and the translational problem. Okay, so basically one will give you the information about the orientation in terms of rotation, and other will give you the information about the location. Okay, so translation will give you the information about the location. Now we have two models. Basically one is the search model, and other is the reciprocal space amplitude. Now when I am talking of a search model, it is directly related to the XY planes. So you have the structure. But when I am talking of the reciprocal plane, then you have the angles, you have the rotations, right? So if you remember, your protein structure will have lot of rotations, you have angles in between. So it's not that unit cell structure alone is going to help it, because if you try to build it, it will give a linear protein structure, and that is of no good use to us. We have to find the exact structure, right? So we have to always think of the reciprocal space, where the rotation and angles are very, very important. So how to score orientation or location of a probe in real space with only reciprocal space data given? Right? So when you just have the angle, with the angle can we come down to the location? Yes, we can do it, and that is where again Patterson mapping or Patterson maps are very, very important with those expressions. So just an example, what I do mean with rotation. So you see here, this is a known crystal form, right? And my crystal, what is the I'm trying to do it, it is something different. You see here, it is slightly different. Now this is basically a rotation has happened, and because of this rotation, now these two are not matching. So I have to understand if it rotates, if I change the angle of rotation, will these models fit with each other? And then comes, along with the rotation, you see the translation, you see the shift here. So from the position, this was with this axis, so these two axes were there, and based on these two axes the rotation has happened in this direction, right, at a same position. But in this case, in the translation, what has happened, your target molecule, you see here, it has moved from position A to position B, and here you have both the effects, you have the rotation effect, you have the translation effect at the same time. So you have to understand these two factors and how we can do this. Yes, as I said, with growing number of people working on this protein structures, you have over a year increasing number of more and more proteins. You have a database. From the database you find a similar 3D structures, and this is a database where you can find out your protein structures. So just a very what is it, diagrammatic representation. Suppose this is what, this is a hand, I think everybody will understand, and this hand has lot of not lot of 5 fingers. We know the structure of this, right? Now once we are trying to decipher, what we are getting is, we are getting information in bits and pieces, right? We are getting information in intensity, we are getting information from the phase, but what we are not able to do is get a whole idea, this is hand or this is something, right? So we have these informations in bits and pieces, and what we try to do is, we try to fit them into known conformations. So for example, we know the structure of our hand. In our hand, we know this is how the representation is going to be. Now, if we have one or two parts, or all the parts maybe of this, we try to see what is the best fit possible to get that structure. Once we get that structure, what we try to see is basically the intramolecular and intermolecular changes, right? So that is what the Patterson method says, that once we have the hand, we see, you see it's rotating in different. So this hand has moved from this here, now this has moved on an angular basis. Now what we see here is basically intermolecular and intermolecular changes. Now in this crystal, you see this is only one plane, XYZ we were talking of. But when you talk of UVW, you see the changes with respect to all the angles have been taken care of, and that is why this angle will give us a better understanding about the orientation in terms of rotation, in terms of translation, both. Okay, so how do you obtain this? We obtain is, there's basically 3 methods I'll grossly discuss today. The first method to obtain a phase information is, it is only possible if the structure of a very similar molecule is known and at least 25% of the sequence identity. So what does that mean? I have a structure of a very similar molecule, and it may be a very close homologous molecule, or it may be a mutant, or it may be another form native also. So what I have to do is, whatever protein, suppose I am talking of a protein, I will try to find out a similar structure, similar molecule protein, very good if it is a close homologous molecule, and it should have at least minimum 25% sequence identity, right? Now once I have found it, what I'll do is, I'll calculate the structural factors, that are F function, right? So the F function of this known molecule, I will find it, I will try to find it, and once I have found that value, what I'll do is, I'll compare with the data set of estimate phase for known structure. You get the point? So what I did is, I calculated the structure factors, okay, for known molecule, and then compared with the data set to estimate the phase for known structure. Correct? So step by step, first the structural factor, I calculated it, or before that I have a structure. I'm trying to find a very similar looking structure. It may be a homologous protein or it may be a homologous structure which needs to have at least 25% sequence identity. From that known structure, what I'll try to find is the structural factor and calculate that structural factor F. From this known structural factor, what I'll try to find out is I'll find out or calculate the phase value. So phase calculation of this known structure, I got that, right? Now use this phase information together with the structure factor information and try to see what is the observed structured factor from the electron density map which I collected, right? So what I had is I tried to find out a similar structure. I calculated its F, I calculated its phase value, and I had that value. And from my structure, from the electron density, I can also calculate the F value, right? Because I am missing only on the phase value. I do not have problem with the F value. So this F value of the observed and the F value of the structure or the homologous structure, I can compare easily. If this gives me a very suitable comparison, then yes, jackpot. Yes. So your phase value can also be applied to your the F value which you have calculated from the electron density, right? And then what you have to do? Then the job is pretty much streamlined. You got the basic structuring, you have to refine it, you have to improve it, and then you see how best or how refined structure you have got at the end of it, isn't it? So this is the first method. Okay, now coming to the second method. The second method is multiple isomorphous replacement. So this is called MIR. Okay. So in MIR, what will happen is we have to obtain, the idea is again simple, we have to obtain the phase information. Okay, so here we are using crystals containing heavy atoms at specific positions. Okay, the difference is here we know we are comparing with the crystals having heavy atoms at specific positions. So these are isomorphic crystals as well as crystals of native protein. So that will be a combination basically, right? But the idea, the main important thing is having heavy atoms at specific positions, right? Now heavy atoms strongly will diffract the X-rays. So these heavy atoms, why we are putting these heavy atoms at particular positions is these heavy atoms will strongly diffract the X-rays. So we know the positions of this heavy atoms, and the pattern coming out or expected to come out can also be predicted. Okay, the difference data set of heavy atom derived and native crystals gives structure factors of heavy atoms only and is equal to the limited data set. Now I have the native, I have also the heavy atom along with the native protein. Now if I remove the information of the native protein, I am left only with the informations which are diffracted by the heavy atoms, isn't it? So only the heavy atom signals I am left with, I am removing the rest of it. So I got it. Now can this information be used to determine the position and phase of heavy atoms? That's the challenge. Now see, our idea is to decipher the phase information. How we are going to do it? First, find a structure. What is the structure's F? What is the structure's phase? And then from the phase value, you see the match with the F, and then you find that, take that phase value for your structures also. That is one method. In this multiple isomorphous method, you have a structure, similar structure, but in this similar structure you know the positions of your heavy atoms. So you have positioned heavy atoms at particular positions, specific positions. Now you have the native protein, along with the heavy atoms, and you take the data. You know the positions of your heavy atoms, right? So you subtract the native protein data, and you are left with only with the information of the heavy atoms. Now only with the information of the heavy atoms you try to find out the phase information. right? So determine the position of them and determine the phase of these heavy atoms. Once you have understood that, okay, you can definitely transfer that information onto your structure. So at least 2 heavy atom derivatives to obtain enough information to estimate the phase of native data set and to solve the structure. So you need to have minimum 2 heavy atoms. That is how you can do it. Okay, so this is multiple isomorphous replacement. Isomorphous multiple, why? Because you are at multiple positions, at specific multiple positions you are replacing or you are putting heavy atoms, and that is why it is called multiple isomorphous replacement. Then comes MAD. So please don't get mad because it may be a little bit monotonous for you. Okay, so multiple anomalous dispersion. Now you have anomalous dispersion in multiple positions. This is also used to obtain the phase information. How? We are using one crystal containing heavy atoms, the same as the previous one, at specific positions, as well as the crystal of the native protein. So the starting point of the taking a crystal of the native protein, taking a crystal containing heavy atoms at specific positions is same for both the cases, for MIR and also for MAD. Now heavy atoms not only diffract X-rays, but they also absorb X-rays of certain wavelength. Yes, they will absorb. So we know the diffraction pattern of heavy atoms. We also know that they will absorb a certain portion of the certain wavelength of the X-ray. Now using a synchrotron X-ray source, what we are doing is diffraction data are generated at different wavelengths of the heavy atom crystal. Okay, so at different wavelengths or modulations of the X-rays are being done, and based on this the diffracted data are generated for different wavelength modulations for the heavy atom crystals. Okay, now different data sets can be obtained and used to obtain the phase information similar to multiple isomorphous replacements. So based on this, what you're doing is we are getting the phase informations, and similar to what we did, the same simulation what we did in case of MIR, we will be doing the same simulation in case of multiple anomalous dispersion, right? So the only difference is here in this case we are using different wavelengths or slight modifications in wavelengths of the X-rays. Okay, so X-rays, if you remember, they are of a range, and that within that range of the X-ray wavelength we try to modify the wavelength slightly and get different diffraction data out of your heavy atoms which are located at specific positions. So what we get is we know that we know at what particular wavelength it is absorbing, and we know what is the diffraction pattern, and then find out the phase information out of it. Okay, so how do we do it? Basically, how do we get that from a native protein to a heavy? So heavy metals are incorporated into the proteins by soaking in metal ions, okay, or by incorporating it's methionine with selenium instead of sulfur, right? So it is selenomethionine basically. Okay, so this is incorporated, and instead of a sulfur you are giving selenium here. Now different metals absorb X-rays, that we have seen by choosing a wavelength that the metal absorbs. Positions of the metals can be determined by the holes, and they leave at the diffraction data. So where there will be an absorption, there will be a hole, there will not be a spot, and then we can find out at this particular wavelength they are. So from there, from the pattern of this we can find out the information, phase information. So the position and the diffraction data will be calculated as per the previous MIR. Okay, now obviously there will be a pros and cons with all these methods. So the good and bad is you are not using, for MIR and MAD case, you are not using a native protein or native crystal. So no problems with isomorphism when using heavy atom derivatives. Okay, that is, I can say it's good. Now selenomethionine is introduced, and introduced in many proteins, as we saw in the protein sequences, they are put into it, and they are used, or they can be used as magic bullets. Yes, because they are doing the job for you, right? So these magic bullets will give you the information. The method of choice to have a de novo structure solution in macromolecular crystallography. When you are doing it for the first time, de novo, then this is the method of choice which is widely being practiced. Now the signals are small in comparison to those of isomorphous replacements, so data have to be good, right? So if your signals are small, so signals has to be good and clear. If your signal is not good, then it will be a problem. In MAD, have to collect a lot of data from one crystal, and radiation damage is a problem. So there are side effects because you have to do it in different wavelengths, different angles, so there have to be a lot of data collection, and radiation damage to your sample can also be a chance. So you cannot overlook that issue. You have to take care of it.